Hello, everyone. A very warm good evening to all of you, and welcome to Unacademy. Welcome to this NCERT series, where we have been covering the portion of climatology for the past few classes. And today we are going to cover a very important topic of permanent wind systems. Now, as a candidate, when you come across topics such as the horse latitudes, the doldrums, the easterlies, the westerlies, and the trade winds. Oftentimes, we are unable to imagine how do they move, why do they move, what is the concept behind Coriolis force. We would have ratified endlessly that anything moving in the northern hemisphere bends to the right, anything moving in the southern hemisphere bends to the left. That is what we refer to as the Coriolis force. But why does it act? What is the analogous way to study that? How do we understand it with a simple car or a train example? Let us understand that in detail. And let us understand, even for example, sometimes you hear in the news stories there is a forest fire in North America. Last year, you had the entire region of North America experiencing that forest fire. Why does that happen? What are these mountain winds? What is a loop? Why does it come into existence? That is the overall coverage that we are going to have today. So today's session becomes of prime importance if you want to understand the concept of El Nino, southern oscillation, if you want to understand the concept of a cyclone, if you want to understand even when we talk about the concepts such as Martin-Julian oscillations, etc., in applied climatology, all of that is dependent on your understanding of this chapter. That is why this chapter is of vital importance, and I hope we are able to do justice to this particular chapter, and I hope we are able to understand it and cover it in as great detail. Now, first of all, based on our yesterday's discussion, yesterday we had a discussion about the case of isotherms, temperature inversion. Now, based on that, let us attempt the previous year question, which was asked from that particular topic. As important as it is to cover the syllabus, equally important it is to validate after each and every topic whether we are able to solve the PYQs or not. Otherwise, there is no point of simply keeping on studying. Okay. So, if you take a look at the PYQ, first of all, which of the following is or are the correct inference or inferences from isothermal maps in the month of January? This was a question asked in 2024. The isotherms deviate to the north over the ocean and to the south over the continent. Presence of cold ocean currents, Gulf Stream, North Atlantic drift, etc., makes the North Atlantic Ocean colder and the isotherms bend towards the north. Now, you have to select the correct answer out of this. Which is going to be the correct answer? Remember, yesterday we had discussed about the heating of land and water and how that will influence the bending of the isotherms. So, the first statement, isotherms deviate to the north over the ocean and to the south over the continents, is absolutely correct. Why? Because we have discussed, yes, perfect, Manisha. The isotherms bend polewards when they cross from continents over to the region of the oceans, and then they bend equatorwards. Okay. So, second, presence of cold ocean currents. Now, we have not yet covered the ocean currents. We will be covering it in the later part of this week or early next week. But basically, there you have the presence of warm ocean currents. Remember, when we were discussing about the temperature distribution across the planet Earth, we had discussed one of the important factors determining the distribution of temperature is actually ocean currents. And that is where we had given the example of the port of Murmansk, that how a warm ocean current, that is North Atlantic drift, creates the region as an ice free ocean, allowing trade. So you have warm ocean currents in that area. Let's assume we did not know about the ocean current. Still, here it is talking about that North Atlantic Ocean is colder and the isotherms bend towards the north because it is colder. If North Atlantic Ocean would have been colder, isotherms would have bended southwards towards equator and not northward. So this is basically incorrect. Correct answer is going to be A, that is one only. Okay. Here, basically, if when you don't have the mention of the ocean here, of the hemisphere here, very good question, Deepika. If we don't have the mention as the hemisphere here, you have to observe that in the second statement here, you have the mention of North Atlantic. North Atlantic. So you take the reference that the first statement would also be dealing with the same region. Okay, that is where you have to take that assumption into mind. Okay, I hope that is clear. Now, here, look at the same kind of a question which was asked, and this was the next year. Same question. Observe this. Consider the following statements. In January, in the northern hemisphere, the isotherms bend equatorward while crossing the land masses and poleward while crossing the oceans. In January, the air over the oceans is warmer than that over the land masses in the northern hemisphere. Take a look at this and let me know what the correct answer in this case is going to be. So, here basically, if you take a look at it, read the statement carefully. The first statement is absolutely correct, right? That over the equator, over the continents, they will bend equatorwards. While crossing the oceans, they will basically bend polewards. That is correct. Second statement. In January, that is the month of winter, air over the oceans is warmer because land is going to be colder. It is because of this statement that the isotherms also indicate a bend. So the correct answer is A. So, if we are able to solve this, that gives you an idea that our preparation is on track and we are able to understand the concepts carefully. Okay. Now, having said that, we will have another set of the case of PYQ that we will be discussing after the class based upon our understanding of today's session. An important announcement for all of you: the mapping session on special class, which was supposed to start from tomorrow, the world map, right? Now, in that particular case, we are starting with the portion of Europe. Now, we, due to certain unavoidable circumstances, scheduling issues, we are going to start that session from Friday. The session, mind you, will be starting from Friday, 5 p.m. We will be covering the case of Europe in this particular case, and then we will be moving ahead. It starts from Friday, 5 p.m. Mark that on your calendar. I will share the link on the Telegram channel. All you need to do is join that and ensure that your world mapping is done. Okay? Now, an announcement for everyone. Now, this offer ends today. This is at the cheapest price that we have brought the product for you, where 16,999 is where you have the availability for 12 months plus a free extension. You need to use the code IS English, ensure. And you would already be aware of that. That if you want to prepare for civil services, this is the best group of educators in English medium that you will find. Along with this, we are going to provide you with the answer writing sessions, the previous year question discussion, CSAT, test series, and ensure that the preparation is online. And this is where basically the offer ends tonight. Do use this offer before the price increase happens. We start with the case of the discussion where we left off yesterday. But having said that, I want to touch upon a couple of topics where I feel yesterday we did not do enough justice to it. And that is, yesterday we talked about the case of pressure, isn't it? So, here for the first few minutes, let me elaborate on that concept of pressure, the concept of a high pressure and a concept of a low pressure, why that is created. Let us understand that. Then we will be understanding the different types of pressure created. We will be understanding the factors influencing the wind movement once again. And then after that, we will be moving to the tricellular and the unicellular model of atmospheric circulation. Okay. So isobars is something that we have already covered. Now, we had talked about the case of pressure. What is pressure? Pressure is basically the weight imposed by the air column on any surface. Total weight imposed by the air column on the surface. So, if you consider the planet's surface, you will have the atmosphere above it. Now, any portion of this atmosphere, if you consider the air column in any portion of the atmosphere, it will extend its weight. It will provide its weight on the lower portion. So, that is what is the pressure. Pressure is what? Force experienced per unit area. In class 8th or class 9th physics, you would have studied it. You would have learnt it, never understood what it means. But I hope now we are able to imagine this. Total force which is imposed by the air column on the ground surface, that is what we refer to as atmospheric pressure. Fair enough? Now, when we talk about this air pressure is not consistent everywhere across the planet. What is the average atmospheric pressure that we have? At sea level, under normal conditions, when we talk about the case of the sea level at normal conditions, pressure is 1013.2 millibar. That is the normal atmospheric pressure that we have. 1013.2 millibar is the atmospheric pressure. Oftentimes above it, we refer to it as high pressure. Below it, we refer to it as low pressure. Having said that, please also understand that pressure is quite comparative. Comparative. Meaning what? Let's suppose I have a region, right? Now, in one place, I have the pressure as 990 millibar. Okay. Now, on the face of it, immediately you will conclude that this is the region of a low pressure, right? But imagine if this is place A, few kilometers away from it, I have place B, which has got 950 millibar. So when you compare A and B is the region of low pressure. A is still a region where some air will start to move towards the case of B. Okay. So that is basically why we say that atmospheric pressure is always comparative. It is never going to be absolute. Okay. Now, how does the pressure vary? And why does the pressure vary from one region to another? So, again, if let's suppose I talk about the case of planet Earth. Now, in one particular area, if I have the air which starts to rise, okay, due to heating, due to wind movement, any factor can happen. Let's suppose I have the air which begins to rise in this region. Okay. So the force exerted or experienced per unit area in this particular case will reduce, isn't it? This will be region which will be referred to as a region of low pressure. So in a way, can I come across my first conclusion out of this? That whenever you have a rising air parcel is associated with condition of a low pressure. Always. Now, why do you have a rising air parcel? We will come to it shortly. But whenever you have a rising air parcel, you will have a condition of a low pressure. Now, let's suppose in a nearby region, I have the case of air which is sinking to the ground. This is a region of surplus of air particles pushing against the ground. So this will experience what? Pressure again, a high pressure. So this is a region of high pressure. And that brings me to my second conclusion. What is my second conclusion? Sinking air parcel. Sinking air parcel is associated with the condition of high pressure. I want you to retain these couple of points. We will revisit this couple of points in another 15 to 20 minutes. And then we will discuss why and under what conditions will we have the rising air parcel, under what conditions can we have the sinking air parcel. This is to be retained by you for the next 15-20 minutes. Having said that, now in the region of this sinking air or the high pressure, there is surplus of particles. In the region of low pressure, on the ground, there is a vacancy created because the air has risen up. So, from the region of surplus to the region of deficiency, I will have the movement of particles. This movement of air particles is what we experience as winds. Okay? This movement of particles is what is experienced as winds. Now, the room that you are sitting in right now, you are surrounded with a lot of air. And mind you, the air is at very high pressure, isn't it? Why do I say that the air is very high pressure in your room? Because let's suppose without any protective suit, I put you up in the mesosphere or your thermosphere. You know what will happen? Your body will explode. Your blood will start to come out, and every organs in your skin will rupture. Everything inside will come out. Because surrounding air will be of such a low pressure, your body will be of such high pressure, it won't be able to tolerate. That is why right now you are sitting in a condition of a very high pressure. But you don't experience this. You don't feel the air. When do you feel the air? You feel the air when it moves. And that movement of air is known as the case of a wind. Wind is what is felt by our skin, by our sensory organs, isn't it? Now, this wind can be cold, this wind can be warm, it can have any character. It can be fast, it can be slow, it can have multiple properties. But one thing is very clear about the wind: winds always blow from a high to a low. Winds will always blow from a high to a low. So, always, regardless of the condition, regardless of the temperature, if there is a wind, it will be moving from a high pressure to a low pressure. That is always what happens. Okay? Yes, correct. Aditya, for example, many of the times you would have observed that even few of the people who have the issue of high blood pressure, when they fly in an airplane, and if proper medications are not taken, they have the nosebleed. And sometimes, in very vicious cases, they have the ear bleed as well. Why does that happen? Because your outside pressure is not that high, and everything from inside, your inside pressure is very high. Near the ground surface, pressure condition is very, very high. That is why the airplanes are a pressurized cabin, right? They have very intense pressure which is maintained. Okay. Now, then we come to the case of the factors which impact the wind movement, the direction, the speed, everything is associated with these three basic factors: pressure gradient force or PGF, the Coriolis force, and the frictional force. What is pressure gradient? First of all, what is gradient? Gradient, when you hear in normal terms, it refers to a kind of a slope, isn't it? In geomorphology, we studied that you have a gentle gradient or you have a steep gradient that ends up determining the kind of mass movement that you experience in any region. So when you hear about pressure gradient, means difference in terms of the pressure, different amount of pressure which is experienced. So in different places, pressure is not going to be the same. For example, if I consider different places, if I consider this region as A, if I consider these regions as B, C, D, E, and F, Now, highest pressure is going to be where? In the region of A. That is where you have the surplus particles. All of them are going to exert their weight on the ground surface. Lowest pressure is going to be at the region of F. Least number of particles. Weight exerted is the minimum. So here you have the condition of very high pressure. Here you have the condition of extremely low pressure. This is a gradient of pressure, how the pressure is changing. So this pressure gradient induces a movement of particles. And this movement of particles is what is referred to as a wind. From a region of a surplus to a region of deficiency, that is why you will have the winds which are generated. That is why always remember this, that wind always blows from a high to a low. Okay. Now, let me give you a scenario. Okay. If I talk about two different conditions, two different regions, let's suppose in one region, I basically have one area which has got a pressure of, this is A, 1020 millibar. Another is 990 millibar. Let's suppose the distance between them is 100 kilometers. This is the first scenario. Then I give you another scenario. A, 1020 millibar at a distance of 100 kilometers. I have B, which is at basically 1010 millibar. In both the cases, I have a high pressure and a low pressure condition. Winds will move. But out of 1 and 2, where is the pressure gradient higher? Out of 1 and 2, always the gradient of pressure is higher at 1. Always it is going to be higher at 1. Here the difference of pressure is 30 millibar. Here the difference of pressure is 10 millibar. Isn't it? So wind will always be stronger in the case of 1. Stronger wind. So this gives me another conclusion, that when the pressure gradient is higher, wind speed is also higher. If distance is more, then you compare the pressure gradient in a comparative distance. Pressure gradient is always compared at a comparative distance. For example, you cannot have a comparison that between Srinagar to Chennai, the pressure is changing by 30 millibar, and between Kota and Indore, pressure is changing by 2 millibar. Where will the wind speed be higher? You cannot have that comparative distance analysis. Whenever you need to have a comparative analysis, you need to put the distance as the same. Okay. Now, in this particular case, remember this, that wind speed is always going to be proportional to your pressure gradient force. Greater the pressure gradient, stronger is the wind. Without a pressure gradient, you will never have a wind coming to existence. For a wind to come into existence, you need a pressure gradient. Okay. Now, then we come across another factor, which is your Coriolis force. Now, Coriolis force is what is referred to as an apparent force. Apparent force, not a direct force. What is the meaning of this? For example, Right now, you are sitting, sleeping, standing under whatever conditions you are in. You are not experiencing Coriolis force. Okay. Right now, let's suppose you basically are driving your vehicle down the road. You're not going to experience the Coriolis force. However, if let's suppose a river, an ocean, wind, a missile, an aircraft, any of the free moving objects, if they move from one latitude to another latitude, they will experience a kind of a bending. So, this bending which is experienced is why? It is because of rotation of planet Earth. That's it. Experienced due to rotation of planet Earth. Had Earth not been a rotating object, you would never have experienced Coriolis force in action. So it is experienced because of rotation of planet Earth. But why? Because of rotation of planet Earth. So here, let me introduce you to the concept of the linear speed here. Now, I hope, even though if you have not been of a science background, you have been of a science background, basic maths is something that we would have all studied. We would have studied that speed is equal to what? Distance by time, right? Distance by time. That is what we refer to as speed, isn't it? This is something that everybody knows. Now, with this concept, let us understand the entirety of Coriolis force. So, if you consider this rotating planet, let's suppose we consider the region of equator. Okay. Let us suppose we consider the region of somewhere here. And let us suppose we consider the region here. That is poles. Let's mark different places here. A, B, and C. Okay. Now, in one rotation, what is the distance covered by A? In one rotation, what is the distance covered by B? And in one rotation, what is the distance covered by C? Is what we will calculate. Okay. Now, here, first of all, what will be the distance covered by A? Distance covered by A will be the circumference of the region of equator. That will be the distance covered by A in one rotation. What will be the distance covered by B? In this entire rotation, circumference of this circle. What will be the distance covered by C? C is lying there itself. Regardless of the rotation, C is not changing at all, isn't it? So, can I say in this entire rotation, A is covering the distance of the largest radius? Can I say so? That distance covered by A is maximum. Distance covered by B is less. And distance covered by C in one rotation equal to 0. So dA is greater than dB is greater than dC. I can have this conclusion, right? Now, based on this, if I basically carry out the same kind of analysis, okay, I have C, B, and A. So, speed of A is equal to distance covered by A divided by 1 day. Speed of the region of B is equal to distance covered by B divided by 1 day. Speed of C is equal to distance covered by C divided by 1 day, isn't it? So, based upon this analysis, can I say that speed at A is the greatest, speed at B is less, speed at C equal to 0. So, that means speed of rotation of planet Earth is maximum at the region of equator, reduces to 0 as you reach the region of the poles. Clear? That is the case of speed of rotation. And in reality, that is true. If you consider the speed of rotation at the region of equator, it is roughly around 1050 miles per hour. That is the speed at which equatorial regions rotate. If you consider the speed of rotation of the poles, it is 0.00008 kilometer per hour, almost zero. The speed of rotation is maximum at equator and is zero at the region of the poles. If you have understood this, then if I have an object or a wind moving from A to B, can I say it is moving from a latitude which is rotating at one speed to a latitude which is rotating at a slower speed? Yes. If an object or wind is moving from B to C, again, it is moving between latitudes indicating different speeds, isn't it? This is where we have to basically understand the concept of relative velocity. For example, consider the two trains. Let's suppose I name this as train A. I name this as train B. Let's suppose train A is moving at 40 kilometer per hour. Train B is moving at 60 kilometer per hour. Train B is moving at a faster pace. Now, here what you see is that basically from B, someone shoots the ball, but rather than moving into the goal post, the ball falls ahead. Why? Basically, because B is moving faster. It will always tend to fall ahead, isn't it? So, let us understand certain cases in terms of how this relative velocity actually acts. So, here we take the car example. First of all, if you have two cars, let's assume both of them are moving at the same speed, 20 kilometer per hour. Someone from car A throws a ball. It will reach and will be caught by the person at car B. Oftentimes, when you drive on the road, and that is where you would have seen, you would also have done that maybe. Many people drive together. They ride their bikes together. They have the full conversation. They can pass the materials from here to there. And for you, the other person is almost static because both of you are driving at the same speed, isn't it? So when two objects or when any object moves between the same speed, it is caught, no deviation. However, if car A is at 20 kilometer per hour, car B is moving at 60 kilometer per hour. You throw the ball from car A. By the time it reaches the area of car B, the car would have moved ahead because it is moving faster. So that means any object moving from slower speed to faster speed, slower speed to faster speed. Can I say falls behind? Falls behind. Same speed, no deviation. It is caught by the person in car B. no deviation. Okay? But from slow to fast, it will fall behind, right? What if you basically have car A, which is moving at a faster speed? What we observed in the case of this train example. Here, object is moving from a faster to a slower train. What is happening? It is falling ahead. So, can I say movement from a faster to slower speed? In that case, it falls ahead. Can I say so? That it will fall ahead in this particular case? It is moving from the case of faster to slower speed, isn't it? With this, let us understand the case of the Coriolis force. I don't want you to have any preconceived notion about rightward bending, leftward bending, anything. We will arrive at the conclusion here itself, both for the northern hemisphere as well as for the southern hemisphere. Now, speed of rotation is fastest at A, lesser at B. So let's suppose an object is moving from, or wind is moving from A to B. That means what? It is trying to reach here at this point. But A is moving at a faster speed. What happens when you have a movement from faster to slower? From faster to slower, object will fall ahead, isn't it? So here, rather than reaching this portion, object will fall ahead. Yes? Now, let's consider the opposite. Let's suppose an object is trying to move from B to A. It is trying to reach here. This is the case of the slow to fast, right? Slow to fast, B is rotating at a slower speed, A is rotating at a faster speed. So it is the case of movement from slow to fast. What was our conclusion from slow to fast? It falls behind, isn't it? Rather than reaching here, it will fall behind somewhere. What is this deviation? This is your rightward deviation, isn't it? Rightward deviation. How do we know whether it is a rightward or a leftward deviation? Whenever you have to understand whether it is a rightward deviation or a leftward deviation, always consider the direction of the wind. Imagine yourself to be looking towards the direction of the wind. So you are looking in this direction. Then your right hand side will be the rightward deviation. Your left hand side will be your leftward deviation, right? So if a wind is moving like this, imagine yourself looking towards this direction. Okay, then you will have rightward, right, and left. Okay, so here you can see this is the case of rightward deviation, isn't it? So always in the northern hemisphere, you will have the winds which bend to the right. Always, it will bend to the right. What about the southern hemisphere? An object is trying to, or a wind is trying to move from equator to the to the higher latitude. Again, it is moving from faster to slower. Faster to slower, what happens? It falls ahead. So rather than reaching this place, it will reach here. It will fall ahead. This is the leftward bend, isn't it? If it is trying to move from here, it wants to reach this place, but slower to faster. Slower to faster, it falls behind. This is the leftward bend. That is the case of movement in the southern hemisphere. It is all depending upon the relative speed. Okay. So basically, you will observe if an object wants to move from equator in the northern hemisphere, it will bend to the right. Right? Towards equator, it will bend to the right. What about the region of the poles? Now, what is the speed of rotation at the region of the poles? Speed of rotation is zero. So, difference of speed between, let's suppose, Arctic Circle and pole is going to be very high. That is why deviation is maximum at poles always. Why? Because speed of rotation is zero. So what does that mean? What if the speed of rotation is zero? How do I understand because of this? That means difference of speed from any latitude will be very high. Hence, Coriolis force is maximum. Now, remember, we had discussed one case that at the same speed you have no deviation. So, if I consider the region of, let's suppose, a similar speed, that is at the region around equator itself, a region around equator. Let's suppose 2 degree north and 2 degree south. This is your 2 degree north or 5 degree north and 5 degree south. Now, speed of rotation of 5 degree north will almost be similar as compared to the speed of rotation at 5 degree south. So, if an object tries to move from here to here, it is moving at almost the similar speeds, no deviation. Hence, because it is moving at similar speed, hence no deviation, that is why Coriolis force at equator is equal to zero. I hope this is understood. Yes, this is the most basic and visualistic manner in which you can understand Coriolis force. Your books, any book that you refer to for your GS, this is where they have not done any justice to the students. This is why I want you to stick to this and understand this whenever you have a doubt in Coriolis force. That is why plane flight path are marked. That is a different case altogether. That is the case of a direct circle, right? Or the shortest circle, the great circles rather across planet Earth. But yes, if let's suppose you have to fly from Delhi to Bangalore, your plane will experience Coriolis force. So the plane has to counter that. Okay. If you are trying to fly from, let's suppose, Delhi to Bangalore, your plane will actually fly like this in order to counter for the rightward bend. Okay, that is basically where it will have the case. Okay, even for that matter, you would have seen in military parlance there is a sniper rifle which is used to fire bullets at a distance of maybe 1 kilometer, 100 meters, 200 meters, 300 meters, 500 meters, not exactly 1 kilometer. Now, even those sniper rifles, when they fire at that greater distance, they always keep in mind the Coriolis force bending. Accordingly, they adjust their scopic view and then they fire the bullet. Your missiles, if you fire, even in the case of missiles, they will keep in mind the Coriolis force bending. Rivers, when they move, they also sometimes indicate the Coriolis force bending. Okay, so what is the case of the Coriolis force? Simple. Any object moving in northern hemisphere will bend to the right. Any object moving in the southern hemisphere will bend to the left. At the region of equator, because they are moving at similar speeds, no bending is experienced. Now, also. If wind speed is very high, wind speed is very high. In that particular case, bending will also be more because it will cover greater distance in the shortest possible time. So it will indicate a greater deviation. Okay. Yes, Sudhanshu. Correct. Very good, my dear. So wind speed is very high. Coriolis force is also going to be very, very high. Okay. Then there is another factor which influences the movement of wind, and that is what is referred to as the case of frictional force. What is a frictional force? Friction is the force of resistance. Okay. For force of resistance. When you try to read too much and your mind simply shuts down, that is your mind's friction. So when you have the movement of winds happening across the surface, now these winds will encounter at the ground level, they will encounter the hills, the buildings, the terrain, everything. So the wind speed is going to be very slow. But as you move at a greater height, they do not experience any kind of resistance. So the wind speed is going to be very, very high, right? Wind speed is going to be very high. Similarly, when we talk about the land areas and the water bodies, over the land areas, here frictional force will be very high. Frictional force is going to be very high. So that means over the land area, speed is less. Whereas over the water bodies, you don't have any friction. So the wind speed is very high. That is why whenever you go out into the sea or the ocean, you experience very strong winds, which are able to generate very large waves along with them. Okay. Now, then we come to a very vital concept, that is the concept of a thermal and a dynamic pressure. We have seen, and this is the time when you recall what where I had left you. Rising air parcel creates high pressure. Rising air parcel creates a low pressure. Sinking air parcel creates a high pressure. But why do we have a rising air parcel? Why do we have a sinking air parcel? That can happen because of multiple reasons. One can be the case of temperature. Temperature means what? That, let's suppose a land is heated. When the land is heated, the air will warm up, isn't it? The air will warm up. When the air warms up, it becomes lighter. Yesterday we had discussed that whenever the air warms up, it becomes very light. As it becomes light, it will tend to rise up. Yes. So this is where on the ground surface, it will create a condition of a low pressure. But this low pressure is created why? Because of heating of the ground. So heating has created a condition of low pressure. This is a thermal pressure. Now, let's suppose you consider the polar region, which is frozen. Air is very cold. Air becomes heavy. Colder air is heavy. It will sink. Correct? So it will impose a high pressure on the ground. So here, both the high pressure and the low pressure which gets created is created because of what? Is created because of temperature conditions. So this is known as the condition of thermal pressure zone. Thermal pressure zone. For a long period of time, geographers across the world were aware or thought that pressure can only be controlled by temperature. That is where you had people like Hadley, Halley, all of them, when they provided even the air circulation model across the planet, which was first provided by Hadley. He considered only the condition of temperature driving the pressure changes and the wind movement. Even when Halley proposed the concept of Indian monsoon around 300, 400 years back, At that point of time also, he simply considered the heating and the cooling of the land. Because at that point of time, the idea was that only heating and cooling can create the low pressure and the high pressure. But there is another factor, that is the movement of the winds. This is what is referred to as the dynamic pressure. What is the concept of a dynamic pressure? Understand this. Let's suppose the room that you are sitting in. Now, in that room, if I provide air movement near the ground surface from both sides, you can see the arrows also, air movement from both sides. Now, this air, when it converges, where will it go? It has got no other place to go. It will collide. It will have to rise up. As it rises up, again, it has got no other place to go. It will hit the ceiling and then will move away. So, can I say on the ground surface, I have a column of rising air? And remember, rising air is condition of low pressure. But in this entirety of the discussion, we don't know the room's temperature. We don't have any idea what is the room's temperature, whether it is heating, whether it is cooling, we don't know. So here the low pressure is created purely because of the movement of the wind. That is what is the dynamic pressure, created due to the movement of the wind. Okay? Due to movement of the wind. Now, let's suppose we consider the another condition. That is the inverse of it. Let's suppose from the ceiling, I have the air which is converging, colliding. Where will it go? It cannot break the ceiling and rise up. It will collide. It will start to sink. It will hit the ground. So, on the ground, what is happening to the pressure? On the ground, the pressure is increasing, isn't it? You have a sinking air column. So, here you have a sinking air, and this sinking air is associated with the condition of high pressure. Yes, this is why here again, have we considered whether the room is cold or hot? No, we have simply talked about the fact that air collides, it sinks, it creates a condition of sinking air. And sinking air, that I know, high pressure. Earlier, the air collided, rose up, created a condition of rising air. I know that rising air creates low pressure. Now, this is what can be observed in many places of planet Earth as well. In many places of planet Earth, from different area, the winds appear to converge. When they converge, they have no other place to go, but they are simply pushed up. So that creates on a ground surface a condition of low pressure. So, can I say convergence of air on the ground? Is this clear? Is this being understood by everyone? Creates low pressure. Can I say that? Yes. On the other hand, convergence of air in upper atmosphere means you have sinking air, condition of high pressure. So convergence of air in upper atmosphere leads to sinking air column, and that creates high pressure on the ground. On the ground. Okay. So now we know that pressure, high pressure or a low pressure, can be created not only because of temperature, but because of wind movement as well. So wind movement can also create a condition of high pressure and low pressure. Okay. So this is independent of temperature. That is why, Devendra, we call it a dynamic pressure, right? Because wind movement can change at any point of time. So the pressure region can also change at any point of time. So this is the condition where you have certain areas which get heated. Due to heating, it creates a rising air parcel. Due to heating, it creates a condition of a low pressure. Due to cooling, certain regions will experience sinking air, thermal pressure. When the rise and the fall of air is created because of temperature, thermal pressure. When the rise and fall of air is created only because of the movement of winds, it is your dynamic pressure. Okay. With this much amount of information, we come across the concept of air circulation. I want you to pay attention and listen to this for 2 minutes. Now, you see, for a long period of time, various different geographers, astronomers, etc., and even normal people associated with science, they wanted to understand what is the wind movement across the planet. Okay. How does the wind movement happen across the planet? Now, why did they want to understand that? Now, you see, right now, you have the movie Odyssey, which is doing all the rounds and is becoming very famous. Homer was the first author who talked about the direction of the winds. Odyssey, after all, the movie is about what? I'm not going to give away the climax story or any of those hidden secrets. The entire aspect of Odyssey is how Odysseus, who wanted to get back home after victory at Troy, basically was waylaid because of the winds. So, around 3,000 years ago, you had Homer who talked about it in his book, where he said that winds from the west carries you somewhere else, and the winds from the west have certain properties. Winds from the north have certain other properties. Winds from the east have certain other properties. So, why did the people want to know about the wind? Because that wind could facilitate the travelers, the sea voyage, correct? So, all the captains and the merchants of the ships, now they would be following the wind patterns. You did not have the diesel engines, the nuclear powered ships which could help you move. So the ships would move basically. Why? The ships could move because of the wind, the sails that they had. So when the sailors basically moved from point A to point B, they would always carry a detailed map, and on that map, they would draw the wind movement so that the rest of the sailors and the captains can also understand them. So that is why people across the world were always interested in what is the direction of the wind movement. Way back around 2,500 years ago, when you had Alexander who came to India, while he was going back, he sent couple of geographers and cartographers to follow river Indus and then follow the ships and bring them to Greece. That is where he was interested in knowing the path home. So that is how important understanding the wind movement had been. But for a long period of time, you had the idea that, see, winds will move from a region of a high pressure to a low pressure. But the pressure is only created by the thermal conditions. Heating creates low pressure, cooling creates high pressure. This was the understanding. Based upon this, first model of circulation was provided by Hadley. Hadley provided the circulation model in 1730s, whereby he said that, look, across the planet you have the region that is equator. Equator is heated, will have rising air, Rising air will have low pressure, right? Then poles, very cold. Sinking air will have high pressure. Based upon this, Hadley proposed what is known as the unicellular model of circulation. Unicellular model of air circulation. Now, what was this unicellular model of air circulation? It basically said that look, at the region of equator, there is enough heating, the air rises up, there is a convection current which is created. The air diverges at the region around the tropopause. It will go to the region of the poles where it is very cold, it will sink and it will come towards the region of this particular low pressure because winds always blow from a high to a low. So this is a region of high pressure. This is a region of low pressure. This model of air circulation was accepted by everyone for more than a century. Through the mid eight up till the mid 1800s, this was the model of air circulation which was observed across the planet. It was in the mid 1800s when few American geographers they started to think that look, frictional force is a very important thing. After all, you cannot have a wind which originates from Srinagar and reaches all the way to Bangalore. There will be certain stoppages, hills, mountains, etc., which will not allow the wind to move from Srinagar to Bangalore. So they said the frictional force will be so high, it will never be able to reach that higher distance of tens of thousands of kilometers. And another aspect was understood by the 1800s. By the 1800s, the geographers they started understanding the concept of Coriolis force. So they said that look, even if the air rises at the region of equator, it will bend so much, it will never be able to reach the region of the poles. If an air rises here, let's suppose, it will bend beyond a point, it won't be able to move any northwards. It will start accumulating here itself. And some of the sailors also said that, as per Hadley, surface wind is always moving from equator to the poles. But some of the sailors said that, look, when we are moving across these areas, we are experiencing a wind towards the poles. How come are we experiencing a wind in between towards the poles? So, based on these criticisms, unicellular model was rejected. And what shaped out of it was known as the tricellular model of circulation. So, what is this tricellular model of circulation? Let us understand this. So, basically, if you consider the Earth's surface across various different latitudes, let's suppose 0 degree, 30-degree north, 60-degree north, 90-degree north. Now we know that 0 degree is very heated, right? And we know that 90-degree is very cold. Okay, so here you will have a sinking air, but at 0 degree, the air is so heated up that it will start to rise up. It will start to rise up, right? Pole to equator, then how equator to the poles? This equator to the pole is through upper atmosphere. This is your upper atmospheric movement. Upper atmosphere at the region of tropopause. Okay, this is not on the ground surface. Okay, but anyways, this was rejected. Okay, so concentrate on this model. Basically, what he said, or what is the tricellular model of circulation, is that at the ground surface, at the region of equator, heat is very high. The air will get heated up. Once the air gets heated up, it becomes lighter, it rises up. As it rises up, it will rise up till where? Only up till tropopause, not beyond that. Why? Why won't the air rise beyond tropopause? Let me know. We have discussed it yesterday. Now, after that, it will diverge. It is like hitting the ceiling. Now, once it diverges, very good, Pratima. Once it diverges, the upper air will experience this wind, will experience bending due to Coriolis force, yes or no? Bending due to Coriolis force. It is moving on the rightward bend because it is in northern hemisphere. So here, this will bend substantially beyond a point it won't be able to move northwards at all. So that is where when it is not able to move northwards at all, because of the bend, it will start to sink. Right? After it sinks, one portion goes to fulfill the region of the low pressure. Other portion, as it is sinking, moves towards the region of the poles. And you have the polar air which is also coming. There is a convergence. And this convergence pushes the air upwards. Remember the room example. Here you have divergence. And that is where you have the entire circulation which is achieved in the atmosphere. Now, here, I want you to again retain these. Convergence of air on the ground generates low pressure. Convergence in upper atmosphere, high pressure on the ground. We retain this? Yes or no? Now, based on that, take a look at this. Now, convergence on the ground creates a condition of low pressure. Convergence in upper atmosphere, which pushes the air downwards. Sinking air, high pressure. Isn't it? Here also you have rising air, but this is because of heating, low pressure. Here you have sinking air, but it is because of cooling, high pressure. So now let me know, how many thermal pressure zones do you see in this image? I hope we are able to see here two thermal pressure zones. One is the case of polar high, that is the polar high pressure. Another is the case of equatorial low. That is the condition of low pressure. Both of these are thermal pressure zones. Whereas the remainder of the two, these are not created because of temperature, these are created because of sinking of air. That is why at 30° north, despite high temperature, you have a high pressure sinking air. This is known as subtropical high. Subtropical high. This is known as subpolar low. Both of these are dynamic pressure. Okay. Now there is generation of 3 cells in each hemisphere. That is why this model is known as tricellular model of atmospheric circulation. This is known as your Hadley cell. Hadley cell. This is known as your polar cell. Okay. And this is known as your Ferrel cell. Now, let me ask you a tough question. Out of these three cells, which is the cell which is dynamic cell? Only one, that is Ferrel cell. Now, how many cells are driven by thermal pressure here? You have two cells which are driven by thermal pressure, Hadley and Polar. Okay? Now, on the surface, you will observe the wind movement to be occurring. This wind movement is what are known as permanent winds. Okay? On the surface. So, how do we have this wind movement which is experienced on the surface? So, basically, let us understand this based on this diagram itself. Now, ideally, from 30° north, one wind moves towards the region of equator, one wind moves towards 60°. So, from 30°, I have a wind which has to move towards 60° and one towards equator. But Coriolis force is also at play. So, this wind will bend rightwards, isn't it? Now, even this wind will bend rightwards because of Coriolis force. Same is the case with the southern hemisphere also. From 30°, one wind moving towards 0°, another wind trying to move towards 60°. They will bend leftwards, leftward deviation. Here also, you will have the case of leftward deviation. Now, from the region of the case of poles to 60°, you have one wind from here, one wind from here. This will bend to the right, and this will bend to the left. All driven by Coriolis force. This is what your entire air circulation is. And winds are basically at upper atmosphere, Coriolis force is going to be much higher, Vinita. You know why? Because at upper atmosphere, you will have the wind speed which is higher. And when the wind speed is higher, that means Coriolis force is also going to be higher. There is no individual scientist who is accredited with the tricellular model of circulation. William Ferrel was one of those who basically punctured the theory of unicellular and sometimes is credited with the concept of the dynamic pressure being accepted across the world. But you don't have one individual. Okay. Now, winds are always named based on the direction of where basically you have the case of the direction of movement. Where do they originate? So these are known as, they originate from northeast, move to southwest, northeasterly trades. Trades. These are known as southeasterly trades. This is coming from west to east, westerlies. This is also coming from west to east, westerlies. This is coming from east to west, polar easterlies. Again, coming from east to west, polar easterlies. Okay? That is basically how you will have the entire case of these permanent winds. Trades for a long period of time did, why the name, these are also referred to as simply the trade winds. Basically, for a long period of time, this would be used in the navigable trade routes as well. Okay, to guide the ships. This latitude is what is also referred to as the subtropical high or the horse latitude. Horse latitude. Why this region, also known as the horse latitude? Because this region is a high pressure. So if you consider the surface, this is the region where you have a lot of sinking air, and then the winds are generated. But if you are an individual, let's suppose standing here, will you experience a wind movement? No. If you are an individual standing here, definitely a strong wind movement. If you are an individual standing here, definitely a strong wind movement. But here, no wind movement. Absolute calm condition. So in Middle Ages, when you had these sailors who would move across large distances, oftentimes they would get stuck in these latitudes because of lack of wind movement, absolute lack of wind movement. Now, in order to save resources, they would oftentimes throw the horses overboard because the horses also require food, lot of water. They would throw them overboard. What they would also try to do, many of the times, try to throw a couple of horses together so that basically it would create some splash which would move the ship ever so slightly, and then the people who row the boat, they can carry it forward. That is why this entire name would be referred to as the region of horse latitude. Okay, it is a zone of calm conditions. Okay, now these winds, they move all across the planet. That is why known as permanent winds. That is why known as planetary winds. At the region of equator, again you have a zone of calm. This is known as a doldrum. But here you have multiple different kinds of stories which go about the naming of this. Why? Because if you observe this area, right, you can basically, if let's suppose this low pressure gets diverted north, you can be pushed here also. If the low pressure gets diverted south, you can be pushed in the other direction also. So some of the stories go that basically this was an area where the sailors were never sure whether they are being pushed or they could be pushed towards the northern hemisphere or to the southern hemisphere. But this was also a zone of calm. Why? Because this was a region where you had intense heating and the rising air. So if you are and the winds coming like this. So if you are an individual here, you will experience winds. You are an individual here, you will experience winds. But there's an uncertainty that the winds can come to you also, can carry you anywhere. That is why the name doldrum. Even today, when you, for example, you use it in your English vocabulary, that which is the option that you have chosen. Sir, I'm in doldrums between, let's suppose, sociology or geography or PSIR, etc. I don't know which way to move. Okay, so that is a doldrum. Does rising air at equatorial region influenced by Coriolis force? No. Rising air not influenced by Coriolis force. Anywhere where they move between the latitudes, Coriolis forces very, very high. Okay. Now we come to the case of the local and the seasonal winds. Now, planetary winds or permanent winds, they are present throughout the year and they are present across the planet. But when we say local winds or seasonal winds, means what? These are temporary in nature. Temporary in nature. Okay. And they are basically restricted to a region. They are regional. For example, when you experience a land breeze or a sea breeze, a person sitting in Lucknow will never be experiencing land breeze or sea breeze. It is regional, Chennai, Mumbai, Kolkata, coastal area. Similarly, when you consider Loo, a person sitting in Srinagar would not be aware what is a Loo. A person sitting in Bangalore would never be aware what is a Loo. So they are region specific. And in winter, do you experience Loo? No. So it is season specific as well. So those winds which are not predominant throughout the year, they are restricted to a certain time and a certain space. Those are known as the local and the seasonal winds. Now they are of two types. One is the case of the daily local winds, which occur on a daily basis. For example, you have the case of, so this is how NCRT has explained your entirety of this local winds. Okay, let's have a better understanding. When you consider the daytime, during the daytime, the land area gets heated up much more. Water is comparatively colder. Water takes more time to heat. This is basically what is going to create a comparative high pressure. Whereas this is going to create a comparative low pressure. Winds always blow from a high to a low. So you have a wind moving from a high pressure to a low pressure. This generates a breeze. Why it is known as a breeze, by the way? Why not a wind? Basically, this classification is done on the basis of speed, right? You have the classification of wind, which is done on the basis of speed. Okay. So that is where if the wind is very fast, it will be referred to as a gale. If a wind is very slow, breeze, right? So that is a another scale of parameter for the definition of the winds. We are not going to go into that depth. Okay. So this is what is referred to as your sea breeze. Why? Because it is originating from the sea to the land. So during the daytime, stand on the coastal area, you will experience a wind on your face. A sea breeze is generated. During the nighttime, the land will cool down at a much faster pace, right? So this is where it will be colder, a high pressure. Water will take time to cool down, it will retain its heat. It is warmer, low pressure. Again, winds always blow from a high to a low. So the winds will be blowing from here. This time they have originated from the land, and hence they will be referred to as a land breeze. It is because of this land breeze and the sea breeze that in coastal areas you will never experience extremely warm, extremely hot, or extremely cold temperatures. Always moderate temperature as compared to inland areas. Okay, this is a daily wind. Then again, another kind of daily wind is what you have in the case of the mountain and the valley breeze. Chennai also does not experience extremity of temperature. Chennai is never going to experience 45 degrees Celsius or 48 degrees Celsius. It is the high level of moisture in the air, humidity. Humidity is so high that 34 degrees Celsius becomes almost intolerable, right? 34 degrees Celsius in Delhi, very tolerable. Why? Because the air is dry. So even when you perspire, the sweat will evaporate, your skin will cool down. But in Chennai, air is so humid, even 30 degrees Celsius, your sweat won't evaporate. You will continue to perspire. That is when you start feeling dehydrated. And that is where the weather is considered oppressive. That is why Bangalore, Pune, why are they considered to be so pleasant in the case of Bangalore and Pune? Because these are the geography creates a perfect windy condition in these areas. You have continued movement of winds. That is why extreme moisture, etc., is immediately taken away. So, even if you perspire, taken away, you feel cool. So, that is why the climate is considered to be very livable in the region of Bangalore, Pune, Nashik. These are some of the places in the country where you will never feel oppressive conditions, even going ahead into the future. Right? Now, another daily condition of wind is the case of your mountain and the valley breeze. During the daytime, the mountain tops get supremely heated, higher insolation. This is where you have a low pressure. Valley bottom, comparatively cooler. This is a condition of temporary high pressure. So you have winds moving from valley to the mountains, upslope winds. These are also known as anabatic winds, isn't it? These are also your upslope winds, right? During night time, what will happen? Mountain top is very cold, loses heat very quickly. This becomes a zone of high pressure. Valley bottom still has a warmer air. Remember, we discussed this in valley inversion. This is a region of a comparative low pressure. So that is where you have the downslope wind. Why? I hope by now you would have retained this. Winds always blow from a high to a low. So that is where you have a downslope wind, which creates a condition of a mountain breeze. Okay. So it originates from the mountain, hence mountain breeze. This originates from the valley, hence you have valley breeze. This is also katabatic and this is known as anabat. Okay. So, like that, you have multiple seasonal winds also across the world. For example, during summer conditions, you will have the situation where the region of the Sistan, Balochistan, the area of Pakistan, Thar Desert, etc., that gets heated. You have the wind movement like this during the afternoons because the northern Indian portion also gets very, very heated, right? So, this is what generates Lu. It is the case of a warm local wind experienced during summer afternoons. Okay, summer afternoons. Okay, so that is the case of where it can basically have the temperature of almost 45 degrees Celsius to 48 degrees Celsius. It can be very, very warm. Why does the mountain get colder faster as compared to the valley? Because above it, the air is very, very thin. So there is no heat retention. No heat retention, right? So that is why heat loss is very high. Lu is the outcome of advection. My dear, any kind of horizontal movement of air is advection. Vertical movement of air is convection. Horizontal movement of air on the surface is always associated with advection. So, Lu is advection, trade winds, westerlies, all of them will be the part of advection. Now, here, if you consider this region of Europe during winter months, now tell me, out of the Mediterranean Sea and the region of France and Spain, which will be colder during the winter months? It will always be the region of France and Spain. Water body is comparatively warmer in the winter, land areas are colder. So, this will create a condition of a high pressure. This will create a condition of a low pressure. So, that is where during winter you will have a wind like this, winter winds. This is known as Mistral. Okay. Now here you have the case of the Rockies. We have covered that in the in the mapping session. You have the Rockies here. Now, when you have the winds which come like this, they climb up the Rockies and they move down the slope as well, right? So you have the mountain where the winds climb down the slope. As they climb down the slope, they come to the region from a region of lower density to a region of high density. So, as any wind moves from low density to high density, there is adiabatic compression. That means there is going to be warming. it can melt the snow. This portion of wind is known as Chinook, downslope wind, also known as snow eater. It melts the snow in the region of the eastern part of Rockies. If you consider the region of Alps, they have the southern slope and the northern slope. Here also, you will have the winds which will climb up and will go down. As they move down to the northern slope, again the same event like the Rockies will happen. This is why Switzerland becomes such a beautiful climatic condition right during the autumnal months. This is known as cone. Okay. Then basically here again you have the mountain systems, a couple of mountain systems. You have the Basin, Sierra Nevada, etc. Here you have the downslope winds. As they come down slope, they will get extremely heated. That heated wind can cause dry condition and fire. That is known as Santa Ana, which is responsible for lot of forest fires. Okay, so this is the case of Santa Ana, right? So they are katabatic winds. They occur in the early spring. They come down the mountain, right? This is how they basically move to the canyons and the mountains in the region of the Colorado Plateau, etc. They approach at a speed of almost 100 miles per hour, and that is where this high speed wind can always fuel forest fire. That is why the region of California becomes so prone to the region or the condition of forest fire. Like that, you have multiple different local winds in different parts of the world, right? So I hope this is a chapter which is understood in great detail. Okay, if you have understood this, let me know in the comment section. But before that, let us solve this PYQ, which is based on this topic. With reference to Coriolis force, which of the following statements is or are correct? It increases with the increase in wind velocity. It is maximum at the poles and is absent at the region of equator. Which is the correct answer in this particular case? A simple question here, right? So it increases with the increase in wind velocity is correct. It is maximum at the poles and is absent at the equator is also correct. So the correct answer is going to be C. That is both 1 and 2. Revati, we will start the mapping session from Friday. After that, it is Monday, Wednesday, Friday, 5 p.m. Okay. I'll share the link in the CNA session as well so that you are able to get that, or in my Telegram channel, you will get that as well. Okay. I hope that you are benefiting from the NCRT series. Now, I will leave you with one question. I want the answer to that in the comment section below. Now, which is the local wind which moves through the region of Africa, which is also responsible for causing blood rain in Italian coastline? Let me know in the comment section. We meet again tomorrow for air masses, fronts, and cyclonic formation. Till then, do take care of yourself. Goodbye. Thank you.